Hi all, my name's Fletch. I'm drawing nuts and bolts in FreeCAD and I'm drawing them to the ISO metric standard. So here's one that I have, and if I look in my spreadsheet, I've got an M10 by 1.5 and it's not what I wanted. I wanted an M6 by 1. It's not a major problem though. All I have to do is change the nut and bolt parameters. So in A3, instead of having 10 mil, I want 6. Pitch in B3 needs to be 1 mil. Length of the bolt 8 mil. The thickness of the heads, these are hex heads for both bolt and nut. I don't want 4, I want 3. And since it's an M6, the distance across the flats 10 mil. And there it is. It's as easy as that. And I can come back in a year's time when I will have forgotten how to draw it. And all I have to do is to change the numbers in the spreadsheet. Let me now talk you through my scheme of things. This is my overall spreadsheet layout. I have 2 input areas and 2 calculation areas. The blue refers to the bolts and the red refers to the nut. The input areas take the basic data you start with: nominal diameter, pitch, height, whatever tolerance you want to use, and then for the nut, the width across the flats, the thickness of it, and its tolerance. The calculation areas are in columns, and each grouping refers to a sketch, so that, for example, here, this is the data for the sketch of the bolt body, then the cutter, then the helix, then the head. Over here I have the nut body, the nut cutter, and the helix. The layout is the same for all of them. On the left there's the name of the line that's been drawn, in the middle there's its length, and then on the right it's alias or tag. So for example, I have external radius, 3 millimeters in length, and the tag that will be used in the sketch, ext body R. Over here in the nut section it's just the same, except now the thread is an internal thread, so the tags are int hex, and it would be int hex R. For the helix, int hel p for pitch. The basic data we start with: nominal diameter. Now that's the diameter of the hole that the bolt's going to go through, and the pitch. The nominal diameter I store in A3, the pitch I put into B3, and then, to keep things regular, I move B3 into the bolt column and the nut column. So it goes into B35 and F35, and here it goes into the areas for the helix, so it's tagged ext hel p, int hel p. The remainder of the data: body length into D3, hex head, we know that. Distance across the flats, again I spread it across the bolt and the nut areas. It goes into B45 and F17, and the tags: ext hex F2F, int hex F2F. Similarly for the thickness, same thing. Now to the ISO standard. We need to decide internal and external diameters of the blank bodies, nut and bolt, shapes and dimensions of the cutting tools, and placement of the tools. Here then we have the ISO drawing. It has everything we require: shapes, angles and proportions. Fundamental to the standard is this basic triangle. The triangle, the three sides are all equal in length to the pitch. All angles are 60 degrees, and from it we can calculate the perpendicular height, and that's P cos 30. We store that in E3. Once we've calculated the height, we can find the major diameter and the minor diameter. For the bolt, the major external diameter is stored in F3, and for the nut, the minor internal diameter is stored in E8. We get the proportions from the ISO drawing, and we take 2 in both cases off because we're dealing at both sides of the diameter. We're now in a position to consider our sketches and where to position them. We are going to have 3. First of all, there's the blank body, then there's its head, and finally there's going to be the nut head. The major and minor diameters we have to convert to radii because these are what we're going to use in the FreeCAD drawing. So there's that conversion to do. And then the bolt body, I'm going to position that on a Z-axis, and I position it at 0. But then its head sketch, I move it down whatever height, whatever thickness I'm going to have it. Similarly for the nut, I move it, I position it on the Z-axis. It's the height of the bolt, plus I think I've used a couple of pitches to move it up. So here we have the actual expressions. X body R in B15, as I said, the Z-axis sketch at 0, and X body Z. And then the bolt head positioning, B17 minus B8, and I put that in B44, X hex Z. So you can see what I've done with the bolt head positioning. I've taken the Z coordinate of the body, B17, and I've taken off it the thickness of the head and put it in B44, X hex Z. By combining it with B17, if ever I decide to move the body anywhere, then the head will follow automatically. The nut body blank is just the same, half the diameter to get the radius, int hex R. The Z-axis sketch coordinate, bolt length plus 2 pitches, twice the pitch, and store it in F17, int hex Z. The cutters, I can see 2 shapes, and while we're here, notice that there are rounded troughs. We can and we will do that. From the ISO standard, these are the proportions and shapes for our cutters. They're shown as I draw them in FreeCAD. Notice that they are facing in opposite directions. Also, Vertically, you move vertically, you're using proportions of the pitch. Move horizontally, you are using proportions of the height. It all works because you're using similar triangles. First, the bolt cutter, the Xed cutter. Tags for the sides, and then the calculations for the sides. They're stored in B24 and B25, and using the proportions from the ISO drawing, these are what have to be used. The depth of cut between the long and the short vertical sides stored in B26. Nut cutter, essentially the same, except the proportions are slightly different. The depth of cut still the same, 5/8 of E3, which is the perpendicular height. Rounding the troughs, the blue represents the bolt cutter, the green part of the fundamental triangle. To round the trough, what we have to do is solve this red triangle. Here's a red triangle solved. Adjacent side, length is pitch divided by 8. Angle is 30 degrees. We can calculate then the hypotenuse and the length of the opposite side, which we need, but we don't use it in a sketch. This is for the bolt cutter. The nut cutter, instead of using 8, we use 16 because the proportions alter slightly. Here we have the nut cutter. Now, I don't insert the full circle. I use 2 arcs and join at that central point there. My reasoning there is it gives a unique point to traverse the helix. Calculations, radius is stored in B27 as XR, opposite side in B28, and we need to calculate XD, the depth of cut. Depth of cut is here. Notice it's the distance between the long and the short sides, it's the radius of the arc, and I take off the opposite side. Why? Because the length of the opposite side is included twice. It's once in that long to short and also included in the radius. So I take it off and store it in B29. I position my cutter X coordinate X to X and the Z coordinate X to Z, and I position it according to that central point. Here are the calculations I need for my positioning. It's X body R minus X D, and that gives us where to position the cutter, and it's stored in B22, and I position the cutter 1 pitch length below the body, and it says XZ. The nut cutter is the same, except it's facing in the opposite direction. Calculations are the same, except instead of 8, now use 16. Obviously the cells are different, the tags are now int R. Depth of cut, exactly the same pattern, F29 and int D. Positioning in F22 int X and in F23 for int Z. Tolerance. If you draw your nut and bolt with exactly the same dimensions and then I use a 3D printer, they won't fit. You're simply too tight. So I have to include a tolerance. Now for my bolts, my tolerance goes in C3, and for the nut it's in C8, and I use it, as you can see down here. First of all, notice for the external I subtract, for the internal I add. So if I put, for example, 5 in C3, then 5 over 100 is 5%. 1 minus 5% gives me 95%. So what I do, I use 95% of the nominal diameter. For the nut, you'll notice, as I said earlier, it's I add. So if I've got 5 in C8, I've got 5% there. Adding it on, I get 105%. So my nominal diameter, I'm increasing it by 5%. You can see the effect of this if you look at the sketches, how it moves it in and out. And if you use a 3D printer and print your nut and bolts off, they will fit. Before drawing, let me remind you about the spreadsheet. All the blue column refers to the bolt. Body, cutter, helix, head. Each refers to a sketch. The orange on the right here all refers to the nut, body, cutter, helix. Each refers to a sketch, or rather, in the helix, they refer to features. In FreeCAD, for the bolt body, a body with a sketch in the XY plane needs a circle centered at the origin. It has 1 degree of freedom, it is centered, it needs to be constrained, and this is how I attach the constraint to the spreadsheet. Pressing on that button, typing S, and it comes up SSH, which is the name of the spreadsheet. Choosing it, X, body, R for radius, OK, it's fully constrained. I'm going to attach it along the Z axis, linking it to the spreadsheet again, SSH, X body Z. OK, it's attached. Now I'm going to pad it. Same again. X body, I want height. And there's my body blank. Now the cutter sketch. A new sketch in the XZ plane, and I'm going to sketch in the first quadrant. It requires 2 arcs, and a polyline, and I've purposely drawn so that there are no horizontal or vertical constraints. Joining it together, centers, ends, joining to the polyline, horizontals, verticals, angles, Xed. I want an angle, so it's Xed A. Roughly got my shape. I'm going to pull it together and get it at the there we are. Otherwise sometimes it won't size up properly. So now I'm going to put dimensions in. So verticals first of all. Choosing L for the long side. Okay, there we go. Now S for the short side. I have 3 degrees of freedom left, one of which is the depth of cut, which is a horizontal. And I want a D on the end of that. There's my cutter then. Got 2 degrees of freedom. First of all, my vertical distance from the X axis. Next, Z. It's moved it underneath, moving it across and positioning it now horizontally, so it's from the Y axis. X, there we go. And that's nicely lined up. Fully constrained, I can close it. Now in a position to put in the helix. I can do it 2 ways, but first I'll use a tool up here, a subtractive helix. There it is. Now I'm going to link that helix to the spreadsheet, same way. SSH Xed, but it's helix Xed hell P for pitch. There we have it. Now the height. Hell H. Okay, there's it. It's more than covered. Tell it OK, and I should have a thread. There, I've got my thread. Now for the head. Another sketch in the XY plane. I want to be able to see what I'm sketching, so I'm going to alter my view to a wireframe. I want a hexagon. I want it centered. If I've centered it, I'll have 2 degrees of freedom. I have one of these degrees of freedom is the orientation. I'm going to set that horizontal, and then I want the vertical distance across those 2 points Xed, and now it's hex I'm looking for. Hex height. Oh no, it's face to face, that's it. Fully constrained. Position it, so attach it in the Z position. Xed, hex, hex, Z. There we go. It's going at -4. It's positioned. Pad it. Xed, hex, and I want the height. 4mm, that sounds about right. So that should be my bolt. There it is, I've got it. Now for the nut. The scheme is body, cutter, helix. Tags or aliases int, hex, int and int hell. A new body with a sketch in the XY plane is required. Again, I want to see it wireframe. There we go. And I need two things. First of all, a hexagon centered at the origin. If it's centered, it will have 2 degrees of freedom. It has. And first of all, I'm going to set the orientation. So I want that horizontal. I want face-to-face distance. SSH int hex face to face. Okay, now I want the central section, so it's a circle, 1 degree of freedom, so it is centered. Constraining it, int hex radius. There we go, it's fully constrained. Now attaching it in the Z direction along the Z axis, int hex Z. It's positioned correctly, padding it. Int hex height 4mm, looks about right. So let's view it as is. There we have it then. Now I need the sketch for the cutter. The sketch for the cutter is in the XZ plane. Same as before, except facing in the opposite direction. Now horizontals, verticals, pull that in, and that's looking now something how I want it. Angles now, I'll pull it down a bit. Int A for angle. There it is. I've got 5 degrees of freedom, so vertical distances, int S for the short side, whoops, int L for the long side. I'm left with 3 degrees of freedom, one of which is the depth of cut. Int D, there we go. 2 degrees of freedom, which are the X and Y directions. So, first of all then, the vertical. So this is the distance of that point from the X-axis int int Z, int Z, now the position of the distance of that point from the Y-axis, which is horizontal, SSH int, and it will be int X. Okay, now that's nicely lined up, fully constrained. I can close it. The helix now. The helix is with the sketch on the pad. Selecting the tool. There she goes. Setting the pitch. Int. And it's int, and it's a helix. Int hell P. Oh, we've got it. The height of it. There's my height. Got more than I need, but who cares? Tell it OK, and there's my thread. There is a problem though. And it's this. look at the sketch. The sketch is lined up exactly, so it won't fit. It's going to be too tight, and this is where the tolerance comes in. If I go to the spreadsheet and on the nut, I can do it on the bolt as well, I'm just going to do it on the nut. So the nut tolerance, I'm going to change it to 5%. That's gone to 5%. If I now go back to my drawing and look at the positioning of my sketch, you can see now how the sketch has moved out. My nut and bolt will now fit. I hope this has all been useful, and remember, you'll be able to, after you've done it, come back in a year and do any nut and bolt you want. See you again then, folks.